Good afternoon, I'm Andrew Douglas. I'm Executive Dean and Emeritus Professor in the School of Engineering. And I'm here with great friends and old colleagues because I used to contribute to mechanical engineering, which I leave now to the more junior people who do it much better than I do. So anyway, welcome to this year's Spring 2024 Billig-Croft lecture. And I'm excited to be here with you and with our guest speaker. And this year we are partnering with mechanical engineering, and you would have known that by seeing the title of the talk, right? So a special welcome to all of the mechanical engineering people who are here, particularly the students, for whom this lecture really is probably most important. I'm going to get through some things before I introduce, or I let someone else introduce today's speaker, and that is, I really want to thank Gordon Croft for establishing this annual lecture in honor of his good friend, Frederick Billig. Now, I want to welcome the Croft family. I hope they're on Zoom, but I'm not sure. Anyway, Gordon graduated from Hopkins in '56 with a bachelor's degree in industrial engineering, and then built a remarkable career in finance, including the establishment of the respected Croft Leomeister Investment Management Company right here in Baltimore, and he managed that with his sons, Kent and Russell. What's important to us is that Gordon has a true appreciation for the overall importance of engineering in our society. He thinks deeply about things that are important to our nation, and is passionate about being a catalyst for change. And any of you who've looked at engineering recently know that engineering is a catalyst for change, for sure. Gordon cares about the work being done here and stays involved with our programming and the people here on a regular basis. Gordon's a wonderfully loyal supporter of the Whiting School, and he's done a number of important things, including he provided scholarships for students from his home area of Port Tobacco in Charles County, Maryland, and established graduate fellowships and 3 faculty scholar positions. He's provided generous, flexible support in the school to invest in interdisciplinary programs. And in 2013, the university was thrilled to name Croft Hall in honor of Gordon's many years of commitment and generosity. So thank you, Gordon, and to the entire Croft family for your foresight in establishing this lecture, and of course, for your overall dedication to the Whiting School. So Gordon is always thinking about the most meaningful ways to give back to the school, and this lecture is really one that honors his friend, Frederick Billig. Frederick Billig received his undergraduate degree from Hopkins in mechanical engineering way back in '55, and he went on from there to a stellar career at APL, the Applied Physics Laboratories down the road towards Washington. Right? Sharing the accomplishments of Dr. Billig would take up a full lecture, so we can't do that. We'll just let you know that he was pretty good. He worked in the area of high-speed air-breathing propulsion for advanced flight vehicles, including pioneering work with the Air Force in external burning and supersonic combustion. I think you might have enjoyed talking to him, judging from the talk we're about to hear. So he was a real pioneer and a true giant in his field. In '66, he retired as associate head of and chief scientist of the Aeronautics department at APL. He had a remarkable generosity of spirit and was known to mentor a lot of people. In the spirit of generosity of Frederick Billig, Gordon Croft created this lecture to bring inspirational people to our campus in the hopes of motivating you, our students, our faculty, and our alumni. So I would like to welcome the Billig family who's joining via Zoom. So if you just give a round of applause. And with that done, now the real action begins. Kevin, if you wouldn't mind. Thank you.
Thank you, Andrew. It's a pleasure today, and I'm really excited about the seminar we're going to have. So I'm going to take just a few minutes. We have a unique opportunity here. As you said, Fred Billig was a real giant in hypersonics. Hypersonics are very important these days. And we happen to have 2 of the nation's experts in hypersonics with us today. And so Dave, would you come up? Dave is actually the head of the Air and Missile Defense Systems or sector at APL. And he was very instrumental in helping me contact Rodney and getting here today. And David's actually going to host Rodney and I and a few others out at APL tomorrow so we can continue the conversations. Thanks for doing it. And he actually knew Fred Billig quite well. So would you just set some context?
Sure, just very briefly, after Fred Billig got his degree here in mechanical engineering, he came down and joined the Applied Physics Laboratory in 1955 and began really fundamental work in establishing propulsion technology as it applied to hypersonic technology. A really long time ago, as a very junior undergraduate student at the University of College Park, I took my first class from Fred Billig, who was teaching on an adjunct basis down there. And so since that time, more than 45 years, I've been working in hypersonic. Worked very closely with Fred Billig over about a 25-year time period, both at ATL and after he retired, working for a small company called Pyrodyne. During many of those years, there was an extremely close collaboration between the Applied Physics Laboratory and Virginia Tech, also with a professor down there, Joe Schetz, who Rodney was also connected with. So there's this interesting connection across these universities. I know about a few months before Fred died, I was talking to him. He was very sick at this point, and he was lamenting the fact that he wasn't going to live to see hypersonics mature and fly. And I told him, no, you've already seen it. The technology was already transitioning from laboratories and analysis into flight demonstrations. And what we've seen today is it to explode on a worldwide scene across many nations across the country. And a big part of what's happening around the United States is a result of that explosion that you see. So it's a really fascinating topic area to talk about. Fred was a real pioneer in this, so it's fantastic that we have this lecture named in his honor. Go forward.
Thank you, Dave. So Rodney, it's my pleasure to introduce Rodney Bowersox to you. The first script that I was given lists all of his titles, which is more than a page long. So I'm going to go to the shorter script. So again, that's to talk as well and things like that. So Rodney is the Senior Associate Dean for Research in the College of Engineering at Texas A&M. He's the Deputy Director of Texas A&M's Energy Experiment Station. Most importantly, he's a professor of research at Texas A&M as the University Regents Aerospace Engineering Professor. He also founded and directs Texas A&M's National Aerothermochemistry and Hypersonic Flight Laboratory, and also is well known as being the principal investigator of the JHTO University Consortium for Applied Hypersonics, or UCA, as well. He did earn his Oliver degrees from Virginia Tech, I believe, as well. Right? So, welcome to Johns Hopkins, and thanks for coming to visit us. Thank you.
So I'm going to jump to this slide. Dave, if I would have known you were going to speak, I could have gone to this slide to start with, because I thought also, I didn't break it through GoJets, obviously, and then in '96 when he had his company, he was at Wright-Patterson a lot. I was at Wright-Patterson at the same time. But my memory of Fred Billig, though, is when the aerospace sciences meetings that we used to hold in Reno, Nevada all the time. And you would see Fred, he would have his yellow notebook, writing notes with his stack of papers running from one room to the next room, to the next room, to the next room. He was a lifelong learner. And that was just a great example for all of us. But for y'all, the students in here, I don't want to set the bar too high, but Fred had a patent on a supersonic ramjet missile that resulted from his PhD dissertation. So that's no pressure to think about that. And he worked on lots of things, including jets into a crossflow, which are fuel injector concepts to fuel these machines, because the flow path in here is also supersonic. So it creates a very complex shock-bound interaction, shock-shock interaction, fuel air mixing problem. All the gas dynamics that you really could possibly be interested in are happening in this particular problem. So it's a very interesting problem, and I'll show a few results on that. And then he also was very instrumental in a program called the X-30, or the National Aerospace Plane Program, which is really what brought me into this field back in the late 80s. This was the Ronald Reagan Orient Express. Supposed to be a single stage to orbit, hypersonic, scramjet powered airplane. So his dissertation work that he started as a student, this was a major program. There's a lot of people around the country that have PhDs. I'm looking at one right now that were funded by this program. This was a major program in the country, and Fred Billig is at the top of this. Without Fred Billig, we're not doing these things. And so his impact is amazing. I was lucky I got to know him a little bit. Okay, so when I was asked to give the talk, I'm like, okay, what am I going to talk about? There's fluid mechanicians at Johns Hopkins that are world renowned. So I'm not going to compare and wow them with our ability to do fluid mechanics. So I stepped back and said, okay, I'm just going to present on topics that I thought Fred might enjoy. Or find at least relevant. And then also, I'm going to focus on hypersonic turbulent flows. I know I keep looking back there. I'm sorry. This is my prop. And so this is just keeping me. So I'm going to focus on hypersonic turbulent flows. I guess I should stand here. And just provide a little bit of optimism towards building reduced order models for these types of flow fields. I mean, there's been a lot of skepticism over the years, but I think we have tools today that will allow us to make progress that we couldn't make 20 years ago. And then hopefully inspire a few collaborations with faculty, perhaps students that are here. And I would have to, I can't not acknowledge the sponsors for the work that I'm going to show. AFOSR, ONR, this is sort of a collage from these folks. But most importantly, I want to acknowledge the collaborators and the students. I mean, everything you see has a student's fingerprint on it, including our laboratory, which I'll talk about when I get there. So without the students, and they're all brilliant, I'm sure everyone in this room is a brilliant student as well. They're just instrumental in our success. So the outline for the talk, it's motivation and challenges. I'm not going to spend a lot of time on that. I'm not going to spend a lot of time on the background because I want to get to some of the cool results and show results. So I went a little heavy in results. So I've designed the presentation. So if I'm trying to run out of time, I can skip sections. And so if you see me skip through a few sections, that's just because I'm running out of time, but I designed it that way. But I want to talk about two different problem sets. Problem set one is a hypersonic turbulent boundary layers. And this is more an external aerodynamics type problem. And then problem set number two will be supersonic jet interaction flows. And the common theme between the two is they're both turbulent. They both require either large scale simulations or models. And they also require experimental data to validate. So that's sort of the underlying theme between all of them. And then we'll summarize and talk about some ongoing work. So just a little bit of motivation. Hypersonics is not new. Hypersonics has been around. I like this picture because I work at Texas A&M. So the guy on the bottom left, if you know anything about Texas A&M, you would recognize those boots. That's Frank Molina, and these are Aggie boots. So he was an Aggie, graduated from the mechanical engineering department, went to Caltech, became Von Karman's right-hand man. Aggie, he flew the first hypersonic flight. Okay, this is the Bolt 2 flight test program, which we led out of our laboratory. Bolt 1A and 1B is being led out of APL, but Bolt 2 was led by Texas A&M and Kubrick, along with a lot of help from the Air Force and NASA and other people. But it was a very successful, including APL, it was a very successful flight. And so we're bookending this thing. Aggies are bookending this flight test program. So this is pretty exciting. But there's been a lot of work, a lot of really fantastic work over the years to develop hypersonic flight systems. You know, from reentry capsules to the space shuttle to all of these different flight test programs. I used to have a picture of the X Prime that looks like the the dream chaser shape. That's a beautiful vehicle. So all the things that we're doing now in hypersonics, someone has probably done. So it's pretty exciting. So what makes hypersonics hard? Maybe what makes hypersonics hard, which also it's the same thing. This blue text on the right really does sort of summarize it. But let me tell you what this is. This, and Dave has seen this facility in action. We have a wind tunnel, which I'll show you in a few minutes. We call HXT, the hypervelocity expansion tunnel. And we can generate true flight conditions up to about Mach 15. We're going to push that to Mach 20, 25. This is a Mach 15 shot. And you can see this is the natural emission downstream of the shockwave. And so this model is about 20 inches wide, about 24 inches. It's a big model. It's in a big wind tunnel. And this is just a video showing this, a lot of electrons in there. But this was taken as part of an Aeronautics project that we're doing for Lockheed Martin. But that's just really cool, right? And so that, and if you look at the entire model, that plasma goes off the back. You can see the plasma going off the back of the model. So the turbulent boundary layer that we're studying also has these physics dumped on top of it. So this is a really complicated problem. And I tried to articulate it a little bit here, but when we jump across this shock, for that particular case, it's about 11,000 Kelvin right there. And then it starts to rotationally excite very quickly and vibrationally excite very slowly. Chemical equilibrium, all this stuff happens, and we're about 6,000 Kelvin. Then you're moving into the boundary layer. So a quote from Fred Billig, when he was at Wright-Patterson, the Air Force was thinking about a certain Mach number regime, and I won't go quote the numbers because I remember them very well, but he asked me if I knew the difference between this Mach number and that Mach number. It was about 2. So I said it was about 2. He says, no. Every metal on the planet melts at this higher Mach number. So that was a direct quote. That was sort of who Fred Billig was as a person when it comes to these things. So there's a lot of interesting physics going on in these problems, and we're excited about all of them. Now I'll talk a little bit about viscous flows, because we're going to couple that chemistry with viscous flows. So transition and turbulence are the two big problems when it comes to high-speed viscous flows, and hypersonic vehicles are dominated by viscous effects. Viscous effects are a dominating factor. So what I'm showing here is a transition mode that only really exists for hypersonic speeds, which is second mode transition, and you can sort of vaguely see it. See this rope-like structure? That's a trapped acoustic wave in the boundary layer that will amplify and ultimately break down and lead to turbulence. I think I saw some simulations of this today. And this is what it looks like in the wind tunnel. And this is a Mach 6 quiet tunnel that we operate at A&M. This one is a 2-to-1 elliptic cone. Okay, that was a high fire flight test. And then this structure here, this is the characteristic structure for what's called cross flow breakdown. So what happens is you have the flow wrapping around the model. So in the boundary layer, you get an inflection point, and that creates these vortices that go down the boundary layer. And these themselves then generate shear layers, and those shear layers are what leads to transition. So this is a precursor to transition. This is actually starting to transition on this model. But when it goes turbulent, this is a top-down view. I don't know how well that's on the screen. It's magnificent. Up there, not so great. You can see a turbulent boundary layer. If you zoom in, you can see all kinds of scales in here. So this is a high Reynolds number Mach 5 turbulent boundary layer. And so once it goes through this process and breaks down to turbulence, it kind of looks like this. And then to solve this problem requires, again, resolving all of those scales, which is a really hard problem. And this is a jet interaction. This is for Fred. It shows the turbulent mixing in a supersonic cross flow. This is a fuel injector. This experiment was done in AFRL. We'll talk about different geometries a little bit later on that. So those are the two couple of problems that we're really interested in. So I'm going to talk about turbulent boundaries a little bit more. And really, I just want to brag about this figure. So I saw some great PIV capabilities today. This is a PIV image at Mach 5. What this is a convective velocity plot. So what we've done is subtracted off the convective velocity. And what you're seeing circled here are signatures of these hairpin vortices in there. In this line here, you've got flow going that direction and flow going this direction. This is the stagnation line along this what's called a very large scale structure. This is in a Mach 5 boundary layer. So this is, I think, the first measurement of its type in a hypersonic boundary layer. This was an incredible measurement. It was done by Scott Peltier, a student. He did this a number of years ago. It's just a beautiful image. So I'm bragging about that. I'm just sorry. I have a lot of, it's relevant for you'll remember this figure because we're going to come back to it. Okay. So in terms of modeling of turbulence, and so resolving all of those scales is computationally very expensive, especially if you turn on chemistry. Because I'm going to show you the equation set and how the equation set changes in a few minutes, but when you turn on chemistry, the ability to do direct numerical simulations gets really fun. Because your equation set gets really big. So we have to use reduced order modeling, and this is sort of a listing of the state of the art. And if you go back to the figure I was just on and you plot the mean velocity profile here, you get what's called the law of the wall, parameter sublayer. Can't resolve it quite as well as you can, but we try. Parameter sublayer, this is the temperature profile. All of our models are tuned to give us that. End of the day, they're tuned to give us that. And what we're going to find is that may change for hypersonic flows in a way that we don't predict. So the advantages of these models, they're relatively robust at low speed, really simple to implement. Disadvantage, this near wall behavior is treated. I should point out, for those that aren't in our field, this is like the bottom 1% of the boundary layer. This is really, really close to the wall. And that's a log scale. That's really, really close to the wall. So the near wall treatments are ad hoc, especially for high speed flows. And I'll show you that we can't simulate favorable pressure gradients with any of these models. And then for the heat flux behavior, the current treatment that we use really only gets one component of the vector correct. The other two components are more or less incorrect, and that's just accepted. So this is the state of the art. But there are significant errors. If we start to look at very high Reynolds number cold wall problems, which is relevant to hypersonics, extrapolate this out to a realistic Reynolds number, we're starting to see large errors in the skin friction. You can see large errors in the heat flux. We've got other data that we can't show, but there's very large errors, up to 50% errors in the heat flux for these types of problems. You can see that the temperature profiles are also missed by this. So bottom line with this slide is we've got work to do in order to improve our prediction capability for these types of problems. All right, so that leads to the research objective. Sorry, I pace when I talk, so hopefully that's okay. If it's not, if it's distracting, let me know. And we do love this stuff. And so our objective really is to advance understanding and mathematical treatments for hypersonic turbulent flow. That's for this one. Tamir, if I would have called you, I would have put the transitional results in because that's what we talked about today. We're going to talk about turbulent flows. Our approach is really founded in two steps. First goal is to develop new mathematical treatments because the mathematical treatments require new advancements. The second goal is to create databases with numerical and experimental to validate our ideas or sort out what's wrong with our ideas and fix them. And this figure, I try to summarize it. So this is fluid dynamic fidelity on the x-axis. So we have NVISID to DNS, and then we have, you can think of this as sort of thermochemical fidelity on this axis. Okay, one temperature model, two temperature, and this will make sense in a few minutes, two temperature, three temperature. At the top, we treat every internal state of each molecular species as a species, and we resolve it all. So ideally, we would be up in the right corner there for a model-free simulation. We sort of live on this dashed line right here today. And what we're trying to do is to develop models that sort of push us up and into that direction. So that's sort of the big picture of what it is we're trying to do. We work with a lot of people to try to accomplish this. And what's listed in here are the second order turbulence moments that I'll talk about these a little bit later. For the experts in the room, they recognize all of these. But if you're not an expert, I'll explain what that is in just a few minutes. Okay. In fact, I'm going to explain it on this slide. So, conservation law equations. There will be a quiz for the students. I don't know if they explain. It's there. Anyway, this is the conservation law equations. These are the Favre averaged. We call Navier-Stokes equations. Navier-Stokes is really the momentum equation. We're including mass, momentum, and energy. There's a lot of terms, but the important thing to point out here is when we do this averaging, and the idea behind averaging the equations is let's not resolve all the scales. Instead, let's model the effect of the turbulence on the mean flow and try to get a good answer for the skin friction, get a good answer for the heat flux, get a good answer for the boundary layer thicknesses and things like this. without having to resolve all of those scales. And we can do a couple of different things. We can do full Reynolds averaging or Fabry averaging, and I'm going to use those interchangeably. Fabry means mass-weighted Reynolds averaging. And so I will probably go back and forth between those, but when I say averaging, you know what I mean. Basically average up the equations, and when you do that, because these equations are nonlinear, the convective terms on the left-hand side are nonlinear, you introduce new unknowns, and these new unknowns show up as a Reynolds shear stress there, as full Reynolds averaging. The one above is what it looks like if you're doing large eddy simulation. So that's a large eddy simulation. This is what it looks like for Reynolds averaging. This is the energy flux. I work with energy, not enthalpy. There's some theoretical advantages there. But if you go to hypersonic flows, it looks a little different. That was for low speed flows. This is what the equation set looks like for hypersonic flows. So it's a bit more challenging. So let me just walk through a little bit of this. So we're going to introduce now a species conservation law equation, which has your chemical production terms. You've got your molecular diffusion going on, your turbulent diffusion going on. Now you split the energy up into external energy, translational motion, and electrons, which because of the speeds are so different, you have a separate electron equation. You have internal modes. So you have energy pool for each of the internal modes for all these equations. So then this is what the equation says. If you're running a CFD solver today that's doing high temperature, non-equilibrium gas dynamics, you're solving an equation set that looks like this. Probably on a volume version, but you're solving an equation set that looks like this. And so we have all of these new unknowns to deal with here. And so what we like to do is we like to derive equations for our new unknowns. So we do that. So we take unknowns of the previous set of equations and we derive transport equations for all of those new unknowns. And if you're thinking, okay, problem is solved, I now have equations for all the new unknowns. Tamir's laughing because we can't solve these equations. We can only model them. Okay? Because every time we do this, we introduce new unknowns because they're still nonlinear. So every time you do it, you just introduce a new unknown, a new unknown, a new unknown. So it never stops. So it's a nonlinear set of equations. So we have to model equations. So tell people that's my lot in life is to take very complicated things and try to will them down to very simple things that we can put our heads around and try to make progress with. So that's what we're going to talk about as we go through this talk. But this is the equation set. What's really interesting. Let me talk a little bit about this energy exchange a bit here. So when we add up all of these energy equations, wrong equation set. When we add up all of these energy equations, they have to add up to the overall energy equation. And so we have energy exchange terms, which are up on this slide. These energy exchange terms allow us to account for energy. If you have a collision and you excite vibration in this molecule and you lose vibration in this molecule, you have to account for that in your energy exchange. So those terms over there are how we account for that energy exchange. So you have to do that species by species. We don't do it collision by collision. We're not that good, but we do it species by species for each. And so you have external, M is internal mode, N is species, M is in, you got it. So bottom line, it's complicated. So that's the mathematical foundation. So now I'm going to talk about the laboratory. We're going to go back to the mathematics in a minute, but I'm going to talk about the laboratory next. So with all of that in mind, we developed a laboratory 20 years ago. It's a pretty pretentious title, National Aerothermochemistry and Hypersonic Flight Laboratory. My program officer insisted on the name National at the time, and he was paying the bills. We put National in the title. It's really that simple. And it stuck. And what you're going to see as we go through this, I don't have a whole lot of slides on this, but everything we've built in the laboratory, the thing I'm most proud about the laboratory, they literally gave us, and David's been there, it's a metal building in a ditch by the airport. But they didn't even have air conditioning when we first moved in. So we turned it into a laboratory. So everything you see the students built, wind tunnels, laser diagnostics, we put them all in. So the student fingerprints are on every bit of this. And really, it's one of the things that make me proud about this laboratory. But we really wanted to create a venue, state-of-the-art venue, to support basic and applied research in hypersonics. And one of the corrections on my computers, I listed all the other participants in my laboratory. There's about 15 other faculty members that use this laboratory now. And they're listed on the one that's on my computer. So let me just list the wind tunnels. We got 3 of them in the laboratory. We're designing some new ones as we speak. This is the hypervelocity expansion tunnel. This is the one that's listed top. This was designed and constructed by us in our laboratory. You can see the operating envelope there is the big outside box there. This is very relevant to the conversation before lunch today, that operating envelope. This was funded by O&R. This is Tyler Dean, who was the student principally responsible for making this thing operational. It works. We run it every day. We've run it about 500 times so far. Sitting next to it, this is the Mach 6 quiet tunnel. Came to us from NASA Langley. This is the only one we didn't design and build. Came to us from NASA Langley. It's one of 2 Mach 6 quiet tunnels in the United States. This is what we call the actively controlled expansion tunnel. We did build this one. This is a variable Mach 5 to 8 facility. These 2 facilities share the same infrastructure, and we've run them over 6,000 times since they've been put in place. The stream tube goes around the world almost 4 times. We in our data acquisition, we increment that and we track that. So the stream tube generated goes around the world. So we've flown around the world 4 times at Mach 6 in those facilities. We also do high performance computing to generate DNS solutions, DES solutions, RAN solutions. The idea here is for everything that we cut metal on, we do a computation first. And so we do computations on just about everything. We'll talk more about what you're seeing in the animation in just a few minutes. Diagnostics. One of the things I did when I was department head was twist Dick Miles's arm, leave Princeton, come to Texas A&M. He created a laboratory called the Alamo. You can send him a note about the spelling. I explained to him that was an Aggie joke, just right there, but he didn't care. But Dick is quite amazing, and he's developed dozens of unique laser diagnostic techniques specifically tailored for hypersonic flows. So his laboratory butts up next to my laboratory. We share doors and we run lasers back and forth. 1 in 4 experiments these days is Dick Miles laser diagnostic test that we do. And this is a beautiful flow field that I'll talk about at the end. This is a shock-shock interaction. This is 2 wedges generating oblique shocks, generating a Mach stem. And here we still have that same, this is a Mach 15 shot, that same 12,000, 10,000 degree temperature down there. This is the emission spectra that we measured. We did rotation to fully resolve emission spectra along that line. And you can see all of the different species that are lighting up in that particular flow field. So it's this, we have fun in the lab. So the question that we're going to talk about first is, how do hypersonic flow physics alter second order turbulent transport modeling? I tried to draw a cartoon sketch of the physics. I lifted this figure from this paper. Aguilar, it's a great figure showing the underlying structure in the turbulent boundary layer. These black images are what you'd have in a low speed flow, velocity fluctuations, pressure fluctuations, and a high speed flow is a little bit more. We talked about that mathematically. So this is a highly coupled physics. I mean, you can have surface chemistry. There's a lot of things going on. And that same figure that we talked about earlier applies to every species. And then they talk to each other as well. So this really is a complex problem. So let's look at an example. This is the first theory. So this is theory number 1. I'm going to talk about 2 theories. We'll go through a bunch of examples. So theory number 1, we're going to look at the approximate solutions to the Reynolds stress transport equation. And this one will kind of make your head spin a little bit. That very complicated equation. For this particular problem, we designed experiments that really only introduce 1 extra strain rate. So we have your main strain rate across the boundary layer, then dV dy, so you have a linear dV dy. So it's a 2 strain rate problem. So the question was, and we did experiments. So we measured the boundary layer properties of shear stresses on that curved wall. Upstream of the curved wall with the pressure gradient is 0, you get a Reynolds shear stress that looks like this. Downstream of the curved wall, you get a shear stress that actually changes sign. Velocity profile doesn't change sign. Momentum transfer doesn't change sign, but the Reynolds shear stress changes sign. And for the longest time, I was perplexed by this because none of our models would produce it. So I went to the longer reach rotating version of the Reynolds stress transport equation model. So can we explain this with that model? Because we're really talking about one component in a tensor. It's a tensor. We're talking about one component, so it's really hard to understand that. So I did it. These are the only two non-zero strain rates. I boiled it down to, there's a lot of steps to get to, there's a lot to get here. That I can write a closed form solution for. It's that complicated equation. This is a closed form solution. You do the coefficients, these are the constants, it all comes out of Longeries and Rhodey. Again, we're trying to explain this, and there's two things to keep in mind. As we go, we're in a wall normal coordinate system. Going from the upstream coordinate system to the downstream coordinate system changed the answer to here. The rest there is transport physics. We have to deal with the transport physics there. So we did more experiments with adverse and favorable pressure gradients. Made sure the upstream looked good. I probably went too fast on that, but it doesn't show up so great here, but you can see all that structure in the boundary. It's just beautiful, right? Anyway, so let's go back to this. So we made measurements upstream, make sure we're getting the right answers. Mach 3, Mach 5, did more than one Mach number. This is the law of the wall velocity profile. This is the axial turbulence intensity, transverse turbulence intensity, Reynolds shear stresses, upstream Reynolds shear, different measurements. It's all normalized. So, all right. Again, negative values. This is one of our Mach 3. You can see the expansions coming off of there. That's not much curvature. I'm pretty sure most of our vehicles that we fly will have at least that much curvature. Okay, so none of our turbulence models can get that right. This is the DNS of that same problem, just to show that we're not providing bad data. One at Ohio State did a DNS. Symbols are our experiments. The lines are his DNS. That's the Reynolds shear stress, the negative Reynolds shear stress. You can see all of the axial things, inverse velocities. So we did a good experiment, and they did a good calculation. So let's explain what's going on. So this shows the zero pressure gradient prediction out of the Longeries-Rhodey. Predictions in quotes because we took the experimental data and ran it through the model. So it's not really a prediction. It's actually an evaluation with the experimental data. It goes right through the data with the original Longeries-Rhodey constants. Average pressure gradient does pretty well. Without doing anything, the Longeries and Rhodey gets this outer part. So the Longeries-Rhodey has the physics to get the outer part right, but it misses the near wall. What we found out in the near wall was that the favorable pressure gradient is altering the shape of that stagnation line or that very large scale structure that we talked about earlier on. What this is a convective velocity profile that is conditionally averaged on a vortex sed right there. So this is just the average. Same thing there. You can see this truncated, very large structure. That shows up in the spectra. For the zero pressure gradient, the peak is over here off the curve. Favorable pressure gradient, the peak is over here. So we've fundamentally changed the underlying structure of this turbulent boundary layer. That shows up in that term that's highlighted. We can adjust C7 and sort out what's going on there from a modeling perspective. But again, it's a little bit of curve fitting, but really this is the physics that are going on. So that was interesting. So what the bottom line there, there's a lot more on this slide, is that Reynolds stress transport appears to be able to handle hypersonic flows with pressure gradients, adverse and favorable. But you have to take into account rotation and redistribution when you develop the models. That's the take home out of all of them. So that's one blue box. And throughout the talk, I have a bunch of blue boxes. These are building a story as we go through. Blue boxes are the story. And this is just, again, showing, this is after you rotate it. This is the physics part. The two words. Okay. Okay. I want to make sure I'm not going to get through this. It also works for roughness. Roughness is interesting in hypersonic flows. This is a cross-hatching pattern. This happens naturally on hypersonic vehicles. When they melt, they create a cross-hatching pattern. When that happens, you get a wave structure that reaches out all the way across the boundary layer. So now you have a sinusoidal pressure gradient. The modeling that we do captures that. We capture it both locally and globally. So this is very useful. You can see the You can see the power spectra, again, shifting that peak onto the chart. So it's really interesting how that works. These are PIV measurements. These are measurements, not calculations. This is Reynolds stress production across this boundary layer. So these are really interesting measurements. And you can see the pressure sensitive paint measurements also on the surface compared to a direct. This is a DES, detached eddy simulation of that problem. So it works. Theory number two, a bit faster. We're going to look at the energy. Now we're going to look at high temperature effects. We derive a reduced order form of the energy flux equation. I'm going to skip some steps. This won't be on the quiz. At the end of the day, this is we've taken that energy flux equation and written it as an AX equals B. So it's an algebraic form. So we reduced it down. AX equals B, and we can see where the physics come in. This is that mechanical stuff that we just talked about. The pink terms are the thermal non-equilibrium terms, plasma-like terms. I'll show you some of that. And then the red terms are the chemical reaction terms that show up. So this gives us a closed form model for the energy flux across the turbulent boundary layer. Bottom line here is it works really well for low speed flows, and for flat plates, we've tested it up to Mach 14. DNS data captures it. The better we do at modeling the Reynolds stresses, the better this model does, because it depends on the Reynolds stresses. So this too works. Okay. And this is a DNS that we just recently did. Sorry about that. Something too much. Can you hear me okay? Good. So this is a DNS that we ran on this ONR project specifically to probe that for turbulence statistics. So we've got that DNS, we're probing it. This was run on Lawrence Livermore machines using the Sandia Spark code. I have a reference, but it's not up there. It's on the early. All right. So we also did some plasma experiments, and this is related to some of the work that you're doing. This is a channel flow, so this is what you're interested in. So this is a low Reynolds number turbulent channel flow that wants to relaminarize. And what we're doing, I'm skip some steps here, is we're showing that when we turn on the plasma, we can alter the turbulence in this problem. This is the turbulence intensity. This is the axial component. Transverse component doesn't change. Axial component does, and the Reynolds shear stress does. So thermal non-equilibrium does couple to turbulence. That's important. That's the important take home here, is that we can couple thermal non-equilibrium to turbulence. We also did this at Mach 6. And again, this you're smiling because this is exactly what you're doing. That's why I was talking. We have tripped flow, electrodes generating a plasma, generating a turbulent boundary layer that's coupled to plasma. So let me get to the cool. Although take a second, you can absorb that figure. That's a beautiful for us experimentalists. That is a beautiful figure. So take a minute. Every time we do it, it looks just like that. So this shows which is the PC Mac problem. Okay. But what we've measured down, this is a statement where we're measuring the vibrational temperature, rotational temperature, velocity, as well as fluctuations down here. This shows the rotational temperature. We're even picking up the shock wave across the boundary layer. Remember that second mode we talked about? These trips trigger second mode. This thing breaks down, goes turbulent. It's a beautiful experiment. This shows the boundary layer evolving. You can see that second mode light up there, working its way down. It's turbulent, very turbulent. This is where we're making our measurements at the back station. These are surface pressure fluctuations, by the way, in the boundary layer. So this is a great experiment. I think you're going to find it useful. So what we did, though, again, this is that reduced energy flux equation for the vibrational mode. And we produced, for the first time that I know of, a profile of the vibrational temperature across a hypersonic turbulent boundary. Okay. So now I have data to see if our modeling makes any sense whatsoever. We didn't have that before we did this experiment, so that was really key. And what we're doing, this is still a work in progress. Now what we're doing is looking at because if you look at, we've taken a mission spectra. There's a lot going on here. We have to go out, we have to go and sort out which reactions, which molecules are vibrationally excited, which equilibrium processes and non-equilibrium processes are going on from a chemical perspective, so that we can sort out what the vibrational relaxation time constant is. Once we have the time constant, this is closed, and we can see if this model works or not. So that we're right there, we're doing that work as we speak. Really cool stuff. All right, let's get to I know we have 10 minutes, but I'm going to go over, sorry guys. This is really cool stuff to me. So the second one I want to talk about, this will go quickly, is the fuel injector work. This is for Fred. He studied these problems. So when you inject fuel into these scramjets, you get a shock wave surrounding it, separates the boundary layer, get a lambda shock, get rotating vortices. It's a very complex three-dimensional problem. So the question is, can we model this one, the second order transport model? So we did some calculations on this. This just shows this just shows a global picture of the calculation. This is for a full stress transport model. And this shows a comparison to our measurements. This is Reynolds stress data that we measured across the plume. This is the calculation. It's not terrible. They're on the same scale. Structures are about the same. That's not bad, actually. Vorticity, those two large scale vortices. There they are experimentally, again, on the same scale. So that's actually a pretty good unit, considering all of the assumptions and approximations that have to go into this model. We were surprised by how good that actually worked. We also did detached eddy simulations. Those worked even better. We can get an idea of the complexity of this flow field. But what we really wanted to do, I want to jump to this one anyway. What we really wanted to do, this is close to my get off the stage slide. I'm almost there, guys. Is we wanted to see, can we tailor flow field for these fuel injectors? Because you pay a price. When you inject this fuel into the scramjet, you generate a shock wave. What is a shock wave? It's drag. It's thermal losses. The question is, can we tailor the shocks to do other things besides just provide drag? And so we started tailoring the shape of the injector. What we were able to do is trap a coherent vortex right here. So that coherent vortex could serve as a flame hole, as opposed to what we do now, which is a big hole in the wall for a flame hole. So we've trapped this vortex, and we went to write patterns just to see if we were doing it correct. That's the experiment at right pat. This is our calculation. You can see these structures, it's all there. Everything that we predicted to be there is there. So it worked. And we can also probe these DES simulations for the Reynolds shear stresses, the things that we really can't measure, to help tune those models that we're talking about. So this pays double dividends for us. But this is really interesting. I think Fred would have found this really interesting, because he was interested in jets into a cross flow and penetration, mixing, and all of that. So this was designed to enhance mixing, minimize losses, and trap a vortex, and it did all of them. Next steps, really high enthalpy stuff. We're studying this shear layer. I think for the interest of time, I'll just go through this really quickly. This is that shock-shock interaction that I showed you earlier. This is the wedge, 40 centimeters deep, huge tall mock stem. These are all the measurements we try to do simultaneously. Each shot costs us about $1,700. So we try to get as many things on there as we possibly can for every shot. So you can see all of it. This is a very complicated setup in our lab. And this was Tyler Dean who did all of this. This just shows some results. This shows some planar laser induced fluorescence and some optical emission spectroscopy measurements coming out of there. And you can see that we're capturing what we think we should be capturing. We're capturing equilibrium temperatures around 5,000 Kelvin, which is about the right answer. So we're studying, but what we're studying though, we really want to study, this is a turbulent shear layer. And we want to study that turbulent shear layer. That takes me to the summary, and this is it. So our next DNS calculation is going to be that shear layer. See that yellow box? What's cool about this is there's no walls in there. There are no wall effects to deal with. And our boundary conditions are just the shock jump conditions. Just apply the shock jump conditions, generate the shear layer. Drops there. So that's a simple DNS from a grid perspective, and it is almost a Cartesian mesh. Very simple. That allows us to then exercise different chemistry because we have simple physical DNS. And this just shows that we did design a really cool fuel injector for a scramjet, which I thought he would appreciate for this. I want to thank you for your time, your attention. I know I ran over and I ran around like a madman, but that's just how I do it. I also want to thank Fred Billig and also the Billig-Croft folks for this opportunity to come and speak. So thank you.
Rodney,
Okay.
we started late, so don't worry about going over that. It's fascinating. We'll take a few questions, and then we do have reception afterwards. The only thing between us and food is questions.
It's me.
Questions are important. This was fascinating. Ready? Front row.
Let's see.
Okay, back here.
It seems like you have a pretty robust experimental library of experimental apparatus. Do you feel like you're hamstrung in any way where having more experimental data, more experimental setups, or even more flight tests would be useful? I know that flight testing is getting more and more common. I think there was a Strata launch a couple of weeks ago. Rocket Lab is doing some stuff as well.
That's a fantastic question. And the answer is yes and yes, right? I mean, flight test data is the truth. When you do an experiment in a wind tunnel, give me a second. I'll just talk about it. You do an experiment in a wind tunnel, you always have wind tunnel effects. Most wind tunnels, with the exception of quiet tunnels, have a free stream turbulence level. In supersonic tunnels, what happens is you get turbulent boundary layers, and those structures create acoustic noise that radiate in. That acoustic noise, for example, can just change transition. Not only does it change the Reynolds number or the position of transition, but it can also change the mechanism. You can turn on a different mechanism with the noise. And so flight is truth. We were very fortunate. We got to lead the Bolt 2 flight test program, and that data set is tremendous. We were able to resolve high frequency response PCB sensors on there. And we measured the different modes as they turned on and off and watched it transition. We measured the skin friction, we measured the heat flux, we've looked at things like Reynolds analogy, we've looked at a lot of different things, we've watched the transition fronts move up on it. So that's the truth. It actually compared really well with our quiet tunnel data, turns out. So that's a validation. So now we can use have a little bit more confidence that we can use our quiet tunnels to extrapolate transition to flight, but in a noisy tunnel, not so much the same. So flight data is better, but it's much more limited, right? Here we have all of these instruments. We don't fly these laser diagnostics on huge optics tables, right? And it's very complex, tedious. Sometimes it can take a week just to align the laser. And so it's very complicated. So yes, there's a lot of apparatus, provides a lot of information, but extrapolating to flight requires flight. It's a good question.
Yeah, thanks for giving that great talk. Do you see the role of machine learning and artificial intelligence?
Yes, I didn't mention it. That C7 term I talked about and some of the coefficients in the turbulence modeling, those are ripe to be trained by machine learning. The challenge is like that DNS provided a mountain of data, but it's one data point. So generating enough data to actually efficiently, this is where his work, having the right data sets to train machine learning in a data starved environment as opposed to a data rich environment is really the challenge. But yes, machine learning is, everyone's talking about machine learning for everything, including the problems that we're interested in.
I'm going to ask you a hard question. We were talking earlier about fundamental research of wanting to be connected to people that are building things, doing things that are applied. The types of things you do. Speak to what's motivated by just pure curiosity. You just love this and you just got to figure out why it works that way. How much of this is somebody comes to you and says, I need to know X, so I could do this.
Okay. So I'm going to give you, that's not a hard question. It's actually an easy question.
Because fair.
It's not even fair. It's not even fair because we love all of it. I mean, we just love doing it. And we love building facilities. We love learning how to use the laser diagnostics. rolling up our sleeves and coding, and we design our own novels, we our own novel design codes, we love it all. The fact that it's useful is the bonus, and the fact that people really want us to do it and will pay us to do it is to do it. So you have to have that reach out to somebody who needs it to pay the bills and get the students to get to do this, but we love it. I mean, the students love it. I mean, I get text messages or email messages every time they run a facility. And it sends me a little bit of a data file. So I check. We monitor the health of all of our facilities, and we also provide some data. They're looking at the data piece. I'm monitoring the health of the facility. So that comes every time they run. It's not uncommon to get a run at 10 p.m. It's not uncommon to get runs over all spring break. The students are dedicated. They love it just as much as I do. In fact, maybe even more. So that was an easy question, frankly.
So I'm going to call to a close, but I have one more request. I know the Dean's Office has paid for all the nice refreshments we're going to have. Asked if we could get a couple of pictures of Rodney with students. I'm sure students have questions or comments for him. So come on down and do that before you go get something to eat out there. But let's thank Rodney again when we're